Okay, in section 5.3, we're going to be talking about proving trig identities. Stop talking, please. Try not to be too scared by the P word there. For the most part, students find this topic easier than the simplifying that we've already talked about, because here you know where the end is. With the simplifying, you weren't really sure what the final answer should look like. Here we know exactly what the final answer should look like. So that helps kind of give us a little bit of a goal there at the end to be striving towards. So typically this is a little bit easier maybe than the simplifying, or at least no more difficult. So don't get too worked up. So I'm going to start with just some tips or requirements. So number one is you must start with one side of the problem and finish on the other. You may not perform the same operation on both sides of the equation. So basically what this means is we're going to pick one side, do some stuff to it, and try to end on the other side. We're going to want to pick the more complicated expression and work towards the simpler side of the expression. Now sometimes it may not really be easy to tell which side is the simpler one, or they may not even be like one side and the other side may be equally complicated. But in general, it doesn't matter. In practical terms, it's usually easier to go canceling things out to get something simpler than it is to expand something simple and turn it into something complicated. It can be done in that order, but the tricks that you use are sometimes less obvious than canceling things out would be to generate new things, right? Can be sometimes a little bit more complicated. 3, if you get stuck, convert everything into sines and cosines. So if you get to a point where you're like, boy, I don't know what to do, or I don't know how to start this, not a bad idea would be to just convert everything into sines and cosines. 4 says to combine fractions, we need to get a common denominator. So remember, to add fractions, you need to have a common denominator. 5, the identity a plus b times a minus b equals a squared minus b squared is very useful, especially to set up Pythagorean identities. What's the name of that little identity there? We talked about it in algebra last year. Yeah, it's the difference of two squares. Good. Yep. And we'll use that quite a bit. That's a good one to kind of keep in mind. And then 6 just says always be mindful of your target expression that you're working towards. Oftentimes that'll be really useful in helping you make decisions about which identity you'd want to use to transfer something, or why would I want to multiply the top and bottom of this fraction by this value, or why would I have thought to factor that thing? Oftentimes you'll get clues on what you should do based on kind of what the other side is, what you should be working towards. Okay, so if you don't know what to do, that's another good place to look. Hi, Caden. Just set it over there. Yep, that'll do. Thanks, buddy. Okay. So the rest of our time here, we're going to spend just doing some examples. So the first example we're going to look at is tan of x plus cotangent of x equals secant of x times cosecant of x. Now my suggestion for you guys is I'm going to ask you guys to kind of help me out and make suggestions about what to do. What are you going to probably want to have to look at when we're doing this? Your identity sheet. So if you have that with you, my suggestion would be to take that out and have it out on your desk kind of while we're doing these things, because it'll help you to kind of go back and forth looking at your identity sheet. This is how we get better at remembering what these are or what we can do with them, is to just kind of play along while we're doing things. So again, I highly recommend that you have that out and you're looking at it when we do things. Trevor? I don't have any extras. I've given them all away. But if you go to our PowerSchool page and you find the Chapter 5 materials, it's the first post in Chapter 5, you'll see the download and you can print your own. But I literally have the one left on my desk that I use so that I can say the letters correctly. I mean, I know all the identities by heart. I just don't remember the lettering that I used to like name them or whatever. Yeah, I wish I had a better answer for you, but okay. At least it's there, right? All right. So let's take a look at this first example. So the first thing we should do is decide which side of this identity to work on. We want to pick the more complicated side. Which side is the more complicated side? I heard one or two people say the left side. Does anybody disagree with that? Why is the left side the more complicated side? Because of what? Yeah. So that's the idea here. So if I have two terms, is always more complicated than one term, right? If you think about it like polynomials, a binomial is more complicated than a monomial. So the left-hand side is kind of like a binomial, and the right-hand side is kind of like a monomial. Okay, good. So we're going to work on the left-hand side. What do you want to do first on that left-hand side? So James says let's rewrite those in terms of sines and cosines. That sounds like a good idea. So tangent we can rewrite as sine x over cosine x, and cotangent as cosine x over sine x. So you're going to notice when I do these identity or proving identities, I'm going to work vertically. So the right-hand side I'm going to write once, and then I'm just going to write the equal sign and not recopy it every single step and just do it once at the very end again when they're the same. But I'm going to be working vertically as opposed to when I simplify and I kind of work horizontally, which is a bunch of equal signs strung together. Everybody okay with that idea? Just from an organizational standpoint, I figure it's worth mentioning kind of how I'm organizing my work here. Okay, so we've rewritten tangent and cotangent in terms of sines and cosines. Now what? Let's make a common denominator because we want to add these two fractions together. Good. What would the common denominator be for this? Good. Cosine x times sine x. So the first fraction I need to multiply by sine x over sine x. And the second fraction by cosine x over cosine x. Which would give me this. Everybody see how we got that? Just by making a common denominator. I didn't write down the multiplying the top and bottom by whatever. You're welcome to do that on your papers if that you think that'll help you to remember what we did. But I didn't write that down here. I said it, but I didn't write it. Okay, what now? Maya? Very good. So Maya says that P1 says sine squared plus cosine squared is 1. So the numerator just turns into a 1. That's good. Everybody happy with that? Okay, what should I do next? So we're only allowed to work on one side, but if we look at the other side, maybe it'll give us a clue as to what to do. Maya? Yeah, so we can think about this instead as one fraction as the product of two fractions, right? If I multiply those two fractions together, I still get 1 over cosine times sine. Everybody agree with that? Why did we want to split that up? Yeah, because I know I'm supposed to get two separate identities multiplied together on the right-hand side, right? I'm supposed to get secant x times cosine secant x. So it made sense to want to break that one fraction into the product of two fractions so I could get two identities to kind of shake out of that. Or two trig functions to shake out of that. Does that make sense, guys? And obviously now that we have the two sides are the same, so we're done. That's probably like a low medium, medium, low medium, kind of in that range of difficulty. Some might be easier than that. Some might be trickier. Sometimes the ones that seem really hard really aren't that bad, but it's maybe that what you need to get going in the right direction is not obvious, but it's not like it's a million trillion steps. Sometimes the ones that have a million trillion steps are really obvious what to do, though, and then they're not that bad. So it just kind of varies a little bit, Trevor, from person to person about, like, if you see what to do, they're usually pretty easy. If you don't really recognize what to do, it may not be that many steps, but it may seem hard because you're just like, you don't see whatever the little necessary trick is to get going. You know what I mean? So it's hard to say in terms of, like, how hard was that one. But I would say it's probably, like, there's nothing tricky we did there. Like a medium-ish. All right, let's take a look at this next one. So cosine n over 1 minus sine n equals 1 plus sine n over cosine n. First thing we should do is pick a side that we want to work on. So you guys, which side is the more complicated side? They're kind of both the same. I would probably say the left-hand side, just because of the denominator has the addition or subtraction in it, I think is a slightly more complicated thing than if the numerator has addition or subtraction in it, because at least I can break that up into two fractions if I wanted to. The denominator with addition or subtraction, you can't do that. So I'd probably say the left-hand side is more complicated, but for this problem, it doesn't really matter. And it should, you look at these things and you should probably think there's not much difference between them, right? So let's just, for the sake of argument, say we're going to work on the left-hand side. What do you think we should do first? Okay, so we're stuck maybe. Let's look at the tips that we have and see if any of those stick out. Because there is one of those tips that would be really applicable here. Anybody with an idea of which tip would be the one that's going to be applicable for us? Leonie? Maya? Yeah, so if I notice here, this kind of looks like an A minus B. This one kind of looks like an A plus B. Maybe if I go and I do the other half of the difference of two squares, that'll get something good to happen. You guys kind of notice that now after we've pointed it out? So what we'll do to the left-hand side is we'll multiply the top and bottom of this fraction by 1 plus sine n. Everybody okay there? Now, should I distribute the numerator through? Maya, you shook your head no. Why not? Yeah, if I look at the final form, I need to have a 1 plus sign in it. Why would I get rid of my 1 plus sign by distributing the cosine through, right? It would be best to probably just leave that in like a factored form, like this. Should I multiply the denominator through? Definitely would want to do that, right? There's no sense in not doing that because I know that neither one of those two things should be in the denominator of my answer. When I multiply 1 minus sine n times 1 plus sine n, what do I get? I can use my difference of two squares identity also. You could FOIL it out though. Either way, you're going to get 1 minus sine squared n. We okay to hear? Okay. Now what? Yeah, so James says that he recognizes 1 minus sine squared is the same thing as cosine squared. That's like our modified version of P1. And then obviously we can reduce. And now we have the same thing, right? Ideally, I would like to write one more line, but I ran out of space, so I'm just going to do that. But we were done there, right? So that one seemed a little bit harder. It was no more steps, right? What was the tricky part? Deciding to do this. Once you've decided to do that, though, everything went pretty easy from there, right? That wasn't complicated what we had to do, but if you've never done that before, never seen that happen before, not always easy to come up with that as an idea right from whole cloth. You know what I mean, guys? Part of the point, though, of doing all these practice problems is to force you to see some of these little tricks and situations and add those as like, oh, maybe I can do that. Maybe I should try doing that in some future problem, right? Now that you've seen it once, you might think to try this again. You know what I mean? All right. Let's look at the next example here. Which side should we work on? The left side, this one should have been pretty obvious, right? The left side is considerably more complicated than the right. Everybody agree? Okay. What's the first thing you'd want to do here to the left-hand side? What was that, Maya? I couldn't really hear. Yeah, let's multiply the numerator out and do that difference of two squares. So when I do that, what do I get in the numerator? Yeah, I get 1 minus cosine squared all over cosine squared. And then what do we see? Okay, what identity, James? Good, so I can use the modified P1 to rewrite 1 minus cosine squared as sine squared. Now what? Sine squared over cosine squared is tangent squared. And what was I supposed to end with? Tangent squared. So I'm done. So maybe at first glance this one looked like there's a kind of a lot going on. Well, not so bad. Right? Yeah, not so bad. That one was a pretty easy one, right? Nothing tricky happened there. It looked worse than it was. We're still good? Everybody feels okay? All right, I think this is our last one here. Which side do you want to start on? I would start on the right-hand side also. What do you want to do first? Maya? Yeah, so Maya looked inside these parentheses and said, hey, there's a greatest common factor of sine squared, A. So let's factor that out. I'm going to move the cosine here to the front also, just so it's not like, I don't know. It seems like the more appropriate place to put those factors is right next to each other. And then I'm going to just use a bracket because it was already getting parenthesis heavy there, just to make it a little more clear, the separation. So before we continue on, let's point out that on the left-hand side, I have a sine squared, and the right-hand side, I have a sine squared. So that tells me that I should probably never touch that sine squared again, right? Because I got that part of the answer all squared away. And somehow all of this stuff is going to turn into cosine to the fifth then. You guys see that? And really, because I have already have a cosine there, really that part has got to turn into cosine to the fourth. Everybody agree? Okay. So that's what my goal is going to be here, is trying to get that stuff to turn into cosine to the fourth. What should I do to do that? Anybody with some ideas? Maya? Can you repeat what you said? It was the beginning. It was just kind of quiet. I missed. When you say break it off, what do you mean? Okay. So you're just saying, like, I want to think about it like this. Okay, sure. That's fine. And then what are you going to do with that? But the first Pythagorean identity would be 1 minus sine squared A, not 2 sine squared A. You see the difference there? So you can't use P1 the way it's written there. You could, though, if you wanted to try to do it that way, which is fine. You could think about it this way. So negative 2 is the same thing as negative 1 and negative 1. You can do that. Does everybody see what I did there? Or I just took that and broke it into two separate negative sine squareds. And now if I take that piece, I can turn that into cosine squared. We can do that. How's that sound? That was kind of where you're driving at, right, Maya? Okay, so we can do it that way. Okay. So that helped a little, right? We turned some sines into, we have some cosine squareds going on in there. What else can we do? So we probably won't touch that cosine squared a again. What do you want to do to this other sine squared a, or this sine to the fourth a? Well, based on what you guys have done so far, I have an idea. Let's use the Pythagorean identity on this sine squared a. What's sine squared a the same as? One minus cosine squared a, right? Everybody's okay with that? Now, normally I probably wouldn't want to do that. But what do I know this big piece inside the bracket has to turn into? Has to turn into cosine to the fourth somehow, right? So even though I took sine squared and turned it into something more complicated, 1 minus cosine squared, I'm pretty confident that that's going to be a good idea because I need to somehow turn all these sines into cosines. Does everybody kind of buy that rationale? So we still have to worry about this sine to the fourth a. Ben? Good. And if we then apply that first Pythagorean, we can write that as 1 minus cosine squared times 1 minus cosine squared, right? Does everybody catch what Ben said there? And I'm going to write it that way. Okay, what do you guys want to do now? All we have is like ones and cosines inside the brackets. Let's just multiply this stuff out. Let's get rid of all the parentheses so we can start combining those things together. Because somehow this should give me what? All that stuff in the brackets needs to turn into cosine to the fourth, right? Okay. So I'll start by distributing that negative through. And then when I have 1 minus cosine squared a squared, how do I multiply that part out? Is that just 1 minus cosine to the fourth? What do we have to do there? We have to FOIL, right? That's 1 minus cosine squared times 1 minus cosine squared. Should you take my word for it that it just turns in, that it FOILs out to give this, or do we need to see that? You believe me? Okay. If you don't, we could do it, but if you believe me, I'm going to just let that go because I didn't want to write it down anyways. Okay. Let's combine some like terms here. -1 and +1. Those just cancel out. I have a cosine squared and another cosine squared, so that's 2 cosine squared, and then minus 2 cosine squared, well, that stuff all cancels each other out. And we're left with just cosine to the 4th. And when I multiply it to the other cosine that's sitting out front, I have what I was supposed to get. That took forever. Who's hoping that there was a quicker way of doing this? There is, much quicker, but this was correct. And this would be fine, test or quiz or whatever. This is still full credit. There's nothing wrong with what you did here. This was probably the more obvious way to do this, but there's a sneaky way that we can do this here. So, I'm gonna, is everybody done writing, or do you need a minute still? You guys good? Okay. So let's return back to this step and look at this step. Oops, not this step. This step. When I look at this piece inside the bracket, what I see is a quadratic. I see 1 minus 2y plus y squared, where y is sine squared a. Did you guys notice that? Now that I point that out, it hopefully is a little easier to see the quadratic sitting there. What can we do with quadratics? A lot of them are factorable. And in fact, this one definitely factors, right? There's 2 numbers that multiply to give me 1 and add to give me negative 2. So that's what I would do here. So I have that sine squared a still times cosine a out front. And now this piece is going to factor into 1 minus y times 1 minus y. And if y is sine squared, what I have is 1 minus sine squared a squared. Everybody's okay with that? And I apply P1 to that. And I know 1 minus sine squared a is cosine squared. And then cosine squared squared is cosine to the 4th. And cosine times cosine to the 4th is cosine to the 5th. And I'm done. Maybe a little bit easier than what we did. Certainly was faster, there's fewer steps, there's less writing. But had you never thought, or had you never seen, like, factoring a trigonomic expression like a quadratic before, unlikely you'd think of that as something to do, right? And again, that's why we chose some of these as examples, is we wanted to have like different things and different tricks that kind of come up to help build out a toolbox of things that you can do or things that you can think to do when you encounter some of these problems. In particular, again, for the quadratic, what I'm looking for is a constant, and then the exponents to be twice, one exponent to be twice the other. So 4 is twice 2. You know, if I had 3 and 6, or 4 and 8, or 5 and 10, like, those are the kind of exponent pairs that I'd be looking for to factor like a quadratic, is that one exponent is 2 times the other exponent. And that's helpful. That does happen here from time to time, and it's a good trick to remember. Although if you don't notice the factoring, you can see that we can still get there by using our Pythagorean identities. We just had a lot of them to use. And it got kind of messy, but it never was terribly, terribly difficult. Like, you guys made all the suggestions on what to do there. So, okay. That's all I need to do for today.